Hello everyone, and welcome to our senior project presentation. We are the MicroDev test fixture group, and we're really excited to show you what we've been working on for our senior project. Currently, students and faculty use multiple microcontroller development boards in class for teaching purposes. While teaching, students and faculty alike have to eventually debug either software or hardware related issues for multiple classes. Of these two, hardware has always been a challenge to debug. This is because, unlike software, hardware debugging requires checking physical components on these development boards. This means that debugging hardware becomes quite a lengthy and tedious process. No pre-made solutions currently exist for improving the hardware debugging process. This led to the natural question of, what can we do to make this process more efficient? Likewise, this is the very problem that the MicroDev tester project sought to solve. The MicroDev tester has become an intuitive and informative tool that people can use to get real-time feedback through simply inserting either an Arduino Uno or an STM Nucleo F446RE, plugging the desired development board in, and pressing a single button on the device. The end user can quickly debug hardware and get simple to understand errors displayed to them. Consequently, this allows any student or faculty member the ability to circumvent the hardware debugging process, which once slowed learning of the subject material to a halt. Alright, and now we're going to lead into the mechanical section of our presentation.
Okay, jumping into the mechanical design, here you see the fixture and its exploder view. You have two main sub-assemblies, a large enclosure and a small enclosure. These two housings were merged in the production for 3D printing purposes, which is the image that you see in the top center. The large enclosure assembly can be seen on the left and the exploder view on the right. Some of the components in the large enclosure include an LCD video, LCD power, along with spare USB-A ports, an ESD ground plane to prevent ESD discharge damaging the printed circuit boards. We also have the Raspberry Pi and Bigfoot PCB inside the enclosure with the USB hub. We have 3 GUI buttons to allow the user to interact with the software and the LCD display. And then in the front we have the subject board USB, which interfaces with the subject board under test. Looking at it from the back, we have a friction hinge that controls the angle of the LCD screen. We have a carrying cutout on the right. We have a USB-C power plug and a power switch on the back to control main power. Also, we have a header cover storage area for the configuration not in use, and we also have a tools and spare parts storage bin directly below that. Here you have a sliding USB port cover. In the case that the user would like to get access to the USB ports, they just slide that cover to the left, and when it's not in use, to prevent dirt and debris from getting inside, slide it back to the right. Looking at the small enclosure assembly and its exploder view on the right, it includes some sub-assemblies which we'll take a look at. Before we do that, we have some of the components. We have the alignment guides. The green alignment guide has been removed for the final revision. We have the pushrod hats along with the STM header covers. We have the ejection crank handle on the right and set screw access holes in the front for maintenance. This shows the two different configurations, and the difference is to get from one configuration to the other, you swap the header covers and you swap the header extensions. This was one of the biggest challenges, was the clearances and packaging of these two configurations for the printed circuit board. Here we show a side view of the Arduino configuration. This shows the headers in the header covers, and the bottom left and bottom right show the Arduino mounted and ejected. This shows the pushrod hats and the pin clearance when the ejection rod is in a fully extended position. This shows where the pushrod hats touch off on each of the boards. The ejection crank assembly can be seen on the left and its exploder view on the right. The image on the right shows the pushrod hats at the top. We have the push rods with the return springs over the top of those as guides. We have the pushrod mounting links, the mid-length, the crankshaft, crank housing upper, the crank housing lower. We have the ejection crank handle and the crank handle retention washer. The image on the far left is the assembly in the advanced state, and the center image is the assembly in the return state. And last but not least, since we did have a production run of 10, we needed some fixtures and jigs to be created to make this process go a little smoother. On the left we have a parallel flat machining jig. It allowed us to machine the parallel flats for the set screws. And then we have a push hat mod so that we could press those inserts square into the push hats. The heat set press allowed us to do that perpendicular to the surface we're pressing into, which really helped since there's approximately 100 heat set inserts per fixture. And on the far right we have some of the wiring harness production. That concludes the mechanical design section. Thank you.
We created two printed circuit boards for this project named Bigfoot and Littlefoot. The Bigfoot PCB contains all the integrated circuits the device uses for testing the subject board, including an analog to digital converter, a digital to analog converter, and a current measurement IC. Each of these ICs uses I2C communication with the Raspberry Pi controller. The Bigfoot PCB uses a header pin interface for connecting with the Raspberry Pi, the Littlefoot PCB, and the external push button of the device. The Raspberry Pi operates on 3.3 volt logic while the ICs operate on 5 volt logic. For this reason, logic level shifters were also placed on the board in order to operate the ICs. Our second PCB, named Littlefoot, is used for interfacing the Bigfoot PCB with the subject board. This is achieved using 8-to-1 bidirectional low impedance multiplexers. Littlefoot contains header interfaces for the subject board, which is placed directly onto the header pins, and for the Bigfoot PCB, which is connected via a ribbon cable. The header pin interface was created in such a way that both Arduino and STM development boards can be connected. The Raspberry Pi is used to control each mux individually, allowing for testing of individual pins on the subject board. The analog to digital converter has 10-bit resolution and is used for testing the subject board's supply pin voltages, GPIO output voltage under load, internal pin resistances, and GPIO pull-up and pull-down voltages. Each of our measurement ICs contain capacitors on their voltage supply, which help keep their voltage supply stable and steady. A ferrite bead is also used in order to eliminate any unwanted high-frequency noise. The digital to analog converter has 12-bit resolution. It is used for testing the subject board's logic levels, analog to digital converter and analog pins, and GPIO wake-ups from sleep mode. The current measurement IC is used for testing the subject board's current draw in normal operation and during sleep mode. It works by measuring the voltage drop across a low-valued shunt resistor. The measured voltage drop and resistance are used to calculate the current flowing through the resistor by using Ohm's law. The IC is used to measure currents from 0 to 1 amp with a 10 mA accuracy. For circuit protection, current limiting resistors were used for the DAC to prevent accidentally driving a load or accidentally sinking into the DAC. For testing the subject board's GPIO output voltage under load, a load resistor was chosen to limit the output current to less than half of the pin's rated current. Transient voltage suppression diodes were also used to protect the board from electrostatic discharge. These exist in the places where the user interacts with the device. For example, on the Bigfoot board's USB connector, and on Littlefoot's header pin interface. Lastly, analog switches were used for isolation between the ADC and the DAC. For the PCB design, we chose to create boards with 4 layers, which include 2 signal layers, a ground layer, and a power layer. This structure reduces the size of any potential ground loops, minimizes noise from outside interference, and allows for a more compact design. Test points were placed strategically around the board in order to aid in the debugging process, along with 0-ohm resistors. For the USB connectors, data lines were made into differential pairs with a characteristic impedance within the spec of USB 2.0 standard. Given the standard 1-ounce copper plane thickness, I2C communication traces were made to be 15 mil in size to ensure clean signal transmission. Stitching vias were placed on the ground pores of both signal layers in order to minimize ground loops and noise. Similarly, fencing vias were placed around the traces used in testing the subject board to shield against noise. The PCBs were populated by hand using a stencil. After baking in an oven, through-hole components were then added by hand soldering. One major unanticipated challenge was the size of the muxes that were used on the Littlefoot PCB. The parts were extremely small, which proved to be an issue when the oven didn't perfectly set the part into place. The PCBs were lastly validated through a series of tests to ensure that they met the hardware specifications.
For the software design, everything is brought together using the view, controller, and model methodology. The view will control the graphic user interface. The controller will separate the view and model, as well as take in information from configuration files that will run the tests. The model runs all the command line interface instructions, so it can flash the subject board and also serial communication to and from the subject board. The Bigfoot PCB will all be controlled through a Bigfoot module, and this will run the GPIO digital signals and the button interrupts, as well as the I2C communication for the ADC, DAC, and the current sensing module. All the serial communication to the subject board will be broken into 3-byte data packets, and the last 4 bits of that is for CRC encoding to help us make sure it's accurate. The first byte is for the pin ID, so that helps us map the pin that we want to pin on the board using just a simple 8-bit number. The test value that's returned is going to be the second byte, and if it's going from the device to the subject board, that will be special instructions or a facade test. So it could be digital signals that need to be sent from the board. Test ID is the other 4 bits of that last byte, and that will control what configuration the pin is going to be set to. So to help us identify how things are being configured on the subject board, you can run a facade flag, which will send back information on the value of the pin on the subject board. So the pin ID will send back the value that's actually set to a register, and it will also say what kind of pin configuration is being used. So if it's analog write, analog read, maybe a digital write, it will send back a different value that indicates which one is being used. We also have here a kind of map for the pin IDs, the muxes, and the enable of which mux is being used. That is mapped to the actual name of the pin, as you can see on the right side of this slide here. On the left side, it shows that the key mapping, which is on the right side, has a test configuration file description and a threshold configuration file description. Each of the tests that are being run have to be put into the test configuration file, and there'll be a different one for the Arduino, and there's a different one for the STM Nucleo. The board can auto-detect which of those boards are being connected, so it will also automatically use whichever configuration file it needs for that board. The thresholds also have different thresholds for whichever board you're using, and for each test it needs a threshold value in that file. So here's an overview of the software in the graphic user interface. One of the requirements is a start button. Another one is to save to a removable media, so we have a set of screens for that as well, and obviously to show the results in the detailed results as well. And the rest of it is to make sure that everything fits together and multiple tests can be run. To achieve all of this, I think the most difficult part for the software side was to figure out how to determine what was a software problem and what was a hardware problem. So it took us a while to debug and to figure out a lot of these issues as they were popping up. One of the big issues, I think, was I2C, when we were trying to determine if the code for the I2C was a problem or the actual devices were not correctly populated, and it ended up being a mixture of the two, so it took a while to come to a good understanding on that. As far as constraints of this project, the software has a constraint in wake-up pins. Not every GPIO pin can be used as a wake-up pin for some of the sleep modes. So we have that constraint in the configuration of this, and so there needs to be a better description and documentation of what can be and what can't be used in those tests.
In the end, we ended up hitting our major design philosophies, which are creating an intuitive design that's open source, rugged, and convenient. And, in short, the full design of this project has managed to satisfy all of our requirements and has achieved its goal of giving both students and faculty the ability to streamline the learning process for generations of students to come. Thank you all for your time, and have a nice day.